Hi there. Today we're looking at IMPALA, Scalable Distributed Deep RL with Importance-Weighted Actor-Learner Architectures by Lasse Espeholt, Hubert Sawyer, Remy Munoz, et al. So this paper deals with a new architecture for deep reinforcement learning, specifically distributed deep reinforcement learning. So that means settings where you go beyond one single machine or beyond one single accelerator, like a GPU. So I want to introduce this by showing you this task here. This is called the DeepMind Lab. And the DeepMind Lab is a kind of a 3D environment, as you can see here. These are screenshots where there are very different goals, but some of this, as you can see, are kind of labyrinth-style things where you have to collect apples. Some are platformers where you, I guess, have to jump around and so on, or find objects. So DeepMind introduced this as kind of a reinforcement learning environment. And what you can do, the agent, as you can see here, has a camera. It perceives pixels, and it can get rewards for performing actions. The actions it can perform is it can, walk back and forth, it can jump, it can crouch, it can rotate. So there's kind of a limited set of actions that it can do, but it can move around in this 3D world, and it needs to achieve some goals, right? So that usually this is kind of a good setting for reinforcement learning. And this paper doesn't do a whole lot of new things in terms of reinforcement learning, but it does a lot of things to kind of make it work in a distributed setting. So usually what you would like to do is something like A2C. A2C is Advantage Actor Critic Learning, and it's a very successful algorithm in reinforcement learning. We won't go into this much here, but basic elements of it is what you have are two things. You have a policy, and usually this is called pi. Sorry about that. Usually this is called pi, a policy, that you input your current state, so your current observation at time t, and you want to score an action, right? Action A. Now, you might have maybe, as we saw before, you can walk left, walk right, and so on. So you might have 10 actions or so. So in here, you would put action 1 or action 2 or action 3. And for this, you would get probability distributions over each action. So maybe in this particular state, so each time with the same state. So you would get a distribution something like this, right? So here you should probably go with action 3. And that's your policy function. Policy function pi tells you in this particular state, which action should you take how often. Kind of gives you a distribution. The second thing you want is what's called a value function. So the value function v, capital V usually, you input your state and it will output what the value is of that state. And that's usually termed kind of as lowercase v. The value of the state is, so given, if you're in a maze, right? I'm going to draw a maze from the top here, right? There's you can't reach there, like here. So here is the goal, and let's say you are, you're right here, the green dot, right? And you have the choice of going forward, to the right, or to the left. Now this would be your policy here. Your policy, you would ask your policy, and A1 would maybe be go forward, A2 go to the left, A3 to the right. So your policy would decide what to do. Your value function, however, would decide in each of the states, so where you are plus where you could go, here, here, here. So basically for each state in the system, it would give you a value. In particular, in this case, it would probably give you a very high value here. Like, yeah, this is a good point because you're very close to the goal right here. This is probably not so good a point, and this is a very bad point because you're going into a corner. You're actually moving farther away from the goal. So if your value function is trained well, then you can use that also to assess your situation. So the value function for each state S, it will give you a numerical value of how good that state is in terms of reaching your goal. And the A to C algorithm now deals with the interplay of these. The A to C uses actually both of these in an interplay. So it will use one to teach the other one, right? And this interplay between those makes for a very successful reinforcement learning algorithm. Now, the way A to C does it is, as you can see here, what it does is there are two variants here, synced step and synced trajectories. But in essence, it has to run these episodes, and these here are steps in the episodes. And let's say an episode has 4 steps, before it can do the learning part. And the learning part is here, the orange thing. Once it has done a step of learning, it has to run episodes again, and then it can do learning again. And that's because of a limitation of this, which is called on-policy learning. So in on-policy learning, you always want to have your update step, which is the orange part, to be fed with data. So all of these steps here go into this update steps, and it's necessary that the steps that you make the updates from are computed with kind of the most current version of the agent, right? So that the agent will go into the world, make some steps using its neural network. Maybe I should explain. So the agent, right, is this box, and the agent has this policy, right? And with this policy, as we saw, it will go and it will interact with the world, right, outside of itself. And it will the world will give back observations, and it will then interact again. So it can move a step forward, right? First thing is moves a step forward, and then the world gives it back aha, you are now no longer here, you've moved here, right? And then it's, now I want to move to the left, and the world says, okay, so you're no longer here, you've moved 1 to the left. And this on the right here are the observations, and this on the left here are the actions. And for the A to C, it's kind of necessary that we always have a current version of the policy generating these steps in order to be able to learn from them. And then the next steps also need to be kind of current and to be learned. Now, there have been attempts to decentralize this, and this is exactly what IMPALA does. So IMPALA splits this into multiple workers. You can think of this as different machines. So there is a split here, and these are called actors, and this is called a learner. Now the actors, they will go ahead and they will run episodes on their own, right? Occasionally, or they will run episodes and they will communicate those episodes to the learner. And the learner will continuously here learn. So these orange steps can be made in much more quick succession and don't have to be like synchronized as in the A to C. Here is another way of seeing this over here, and we'll just concentrate on this left thing here. So there is a learner and there are actors, and every now and then the actor syncs its model from the learner. These are different machines, so this can happen over the network. Every now and then the actor gets like an update of the newest policy network, and then the actor will just go ahead and run episodes using that policy, right? Episode, step, without interfering with anything else. And then once it has run an episode or multiple ones, it will communicate this back to the learner. And if all the actors do this, right, the learner gets a whole bunch of these episodes and then can learn from all of them simultaneously. And it can do so in kind of very fast succession, as you see here. So the work is split. Now, of course, you run into a problem. Namely, as we saw in the A to C algorithm, this type of reinforcement learning requires, basically, that you always run the episode with the current model. And that's not the case here, right? The actor may sync the parameters. It may sync the parameters once in a while, but then it will run these episodes, right? When it runs these episodes here, it has no idea, or the learner in the meantime has continually been updating the model, while the actor kind of has an old model. So these episodes here are run with an old model. So the learner, if it tries to learn from this, must kind of correct for this fact. And the big kind of theoretical contribution of this paper is how to correct for the fact that the data you learn from comes from an outdated policy model. And this is what's called V-trace correction. So without going too much into the details here, V-trace correction happens as follows. So what you define are what's called V-trace targets, and these V-trace targets are basically the targets that you train your value function towards, right? So the value function, as we discussed before, that is the thing that tells you how good each state is. And the targets you train this towards, and you're also, by the way, using this V-trace corrections in policy updates, but these are defined as follows. So the V-trace target for step S is the value function at step S plus this correction thing. And the correction thing basically, well, I'm going to break this down some more. So the V at current S is your value function plus, and this is a sum over all future steps over, and this is a discount factor, and this is kind of a delta from one step to the next. So you're in an episode and you've made some steps, right? And let's say we are here, right? This is S. And so your little vs will be whatever your value function says of S plus kind of a correction for each step that you make go into the future, like this. And the main part of these is this here, which is basically the reward at the step plus the difference of the value functions of the steps after it. And what V-trace introduces now is this bit here. And these CI, again, are computed as such. So all of this kind of is very nested. So there's a big multiplication here. It's a very nested thing. But in the very, very, very core of it, you can see the following. These V-trace corrections are a ratio between pi and mu. And pi is the policy of the learner. That is the current policy. And mu is the policy that has been used to generate the episode. And this is truncated by a minimum. And usually the C bar is 1. So let's consider what happens here. What happens is, let's say that mu is higher than pi for a given pair of AI and Xi. What does it mean? It means that in the past, you run an episode, you are in this maze, right? And you're here, right? Now, the goal, let's say the goal is down here. And the action is going over here. That's the action that you're considering here. Now, your mu, which is your old policy that the actor has synced at some point, mu might say, this is very good, right? Because it moves you towards the goal more. But then your pi, the learner has been learning since the agent, the actor, has synchronized the weights. The learner has been learning, and the learner might know, wait, since you have decided this, I have actually learned that this might not be such a good move, because there's a wall here and I'd rather go down here and then over here. So what it will do, since pi is low and mu is higher, it will downweigh this action. And this is how you correct for the fact that there are old weights. By basically downweighing wherever the old policy thought of an action as being worth more than the new policy does. And this is how you make up for the fact that the new policy, you assume it knows better because it has learned more. And thereby you give lower weight to the data points where the policies have diverged a lot. So that's at the core of it. And you can think of, in terms of here, you can think of it as maybe here at this step, you're at a point where the old policy that the actor has updated itself to says we should do action 1, right? But the new policy that the learner has, in the meantime, has learned more, says, no, we should do action 2. And if this is the case, then this whole rest of the episode is downweight, because it is no longer current knowledge, right? And this is not just kind of a heuristic, but they actually do prove that this comes with some guarantees. Especially it reduces to kind of the classic reinforcement algorithms if you assume that mu is always pi, so that current policy is the old policy, and therefore you're in the old setting. All right, so this was a bit of a lengthy explanation of the math behind it, and at the end, what you do is the following. You train your value function using this update. And you can see here, it's simply the gradient of the value function scaled by the thing that contains this v-trace target, right? Then you update your policy in this direction. And this is the classic reinforcement learning reinforce style policy update, where here you have the gradient of the policy, and here you have the weighing by the reward, and specifically here it is the reward plus this v-trace target, and this thing here is a bias correction, or a variance reducing bias. That was terrible. The final form is what's called an entropy penalty, where you want to push the entropy of your policy up such that the agent kind of is biased towards exploring more than exploiting, if you know of the classic exploration-exploitation dilemma. So that's what you do. You compute these v-trace targets, update your value and policy according to these equations, and there you go. So what does IMPALA do specifically in this DeepMind Lab? They have two architectures. First of all, they have this small architecture. Second, they have this large architecture, and they just kind of try it out on these. And they measure how many frames per second they can get in. And you see here, compared to on single machine, compared to A3C, they bring in a lot more frames per second. This is just on a single machine. But then on distributed setting, the scale up also is very significant that they reach. That's because they don't have to wait for other things. They can just go ahead. Everything runs at full speed, basically, and everything runs in parallel. And the fact that some of the information is old is corrected by v-trace. And the last thing I want to show is the wall clock time. I think this is the important plot. In this DeepMind Lab, on over all the tasks, the wall clock time compared to the score. You can see A3C, while it does, increase over time, the Impala variants up here increase in much, much faster wall clock time. So that's the paper. They have a lot of proofs in the appendix, which I'm not going to go over. If you want to give it a try, then it is not called Impala on GitHub. It is called, I think, Scalable Agent. So on GitHub, it is called Scalable Agent, I think. But you'll find it if you search for Impala GitHub or something like this. Other than that, thanks for listening and see you next time.